Hello, I'm Avery Copeland, and I'm going to be demonstrating Classical Conversations Cycle 2 Science Memory Work, Week 20. Namely, what is the second law of thermodynamics? The second law of thermodynamics is heat will always flow from an area of higher temperature to an area of lower temperature. I'm going to be combining this along with Week 23, which is how does heat flow? Heat flows through radiation, conduction, and convection. Now, heat transfer is something that you hear about in science, and that's the scientific term that people use is heat transfer and instead of heat flow. But these two things really complement each other, right? It's true. Heat always flows from an area of higher temperature to an area of lower temperature, and it can do that in three different ways. It can do that via radiation, conduction, or convection, and I'm going to be demonstrating all three of those for you today. What you'll need is some ice cream, 2 Ziploc bags, each with an ice cube in it. The ice cubes should be roughly the same size. 2 sheets of construction paper, or I have craft foam, 1 white and 1 black. I'm going to set these over here to the side. And to start my experiment off, I'm going to put the 2 ice cube bags on the construction paper, one on the black piece of construction paper and one on the white piece of construction paper. Now in class, you'll be doing this in the sunshine, okay? But here, to simulate the sun, I'm going to be using a gooseneck lamp with a 100-watt light bulb in it, because that will also facilitate me being able to do another experiment later. So I'm going to turn on that light now, and I'm going to let it sit. And you can see that there are 2 ice cubes. One is on the white paper, one is on the black paper. They're both roughly the same size, and they're sitting about the same distance from the gooseneck lamp. Okay. So now that experiment just sits for about 15 minutes. Now I have to take one for the team, because for this experiment I have to eat ice cream. Oh dear. So what you'll do is you'll take a small scoop of ice cream, probably about a tablespoon. You'll place a tablespoon in one bowl and a tablespoon in another bowl. And what you're going to do is you're going to coat one of these scoops of ice cream with some milk, okay? That's tough as a scientist, let me tell you. Okay, so I'm going to take this milk here. I'm going to pour some milk over that one. Okay, so it's sitting in milk now, and this one is not. And now comes the taste test. You take a taste of the ice cream not covered in milk, and you see how it reacts with the inside of your mouth. You're going to hold it in between the tongue and the roof of your mouth and feel how cold it feels to you. Then you're going to take a bite of the ice cream dipped in milk and do the same thing. And once again, you're going to press it between your tongue and the roof of your mouth. And what you feel is you feel heat leaving the palate of your mouth and your tongue and going into the ice cream and warming up the ice cream and changing it from a solid to a liquid. Now, you know, this might take 2 or 3 times to be sure that you get it just right. And what you will find is the ice cream in the bowl that is covered in milk feels colder to your palate than the ice cream that's not in milk. The short explanation for that is that, well, you know, when ice cream is made, it is churned. And when it is churned, air is mixed up into the ice cream. And as you probably know, air is an excellent insulator, right? Double pane windows are better than single pane windows. Okay? And that air keeps the temperature of the ice cream from changing quite as quickly. Whereas the milk on the outside of this ice cream conducts heat more readily than the ice cream itself, and that's why the heat transfer from your mouth to the ice cream is faster in the bowl with the milk. Okay, wow. suffer for the sake of science. Okay. So that is our conduction experiment. Conduction between the roof of your mouth and between the ice cream. Okay. Now let's talk about radiation. Well, for radiation, we're going to go back over here to our lamp and our sheets of foam or construction paper. Now, the lamp itself represents the sun, okay, and these represent two different surfaces. You could say that the black one represents asphalt and the white one represents Portland cement sidewalk or something like that, okay? And the sun heats up the earth, but it doesn't do it by touching it, heaven forbid, right? Not like the ice cream and the roof of your mouth, okay, which touched each other and conducted heat from one to the other. This is simply radiating heat, okay? And it's radiating heat to the ice cubes. Now, you know, it's hard to tell. It's only been in here for about 5 minutes, so it's hard to see much difference. So we're going to put this aside for one moment once again and move on to the next experiment, which is namely conduction. Now, I have another supply for this one. I have a homemade pinwheel, okay? It's just a straw and a piece of paper and a foam tag, and you can buy ones that work a little better. Now, if you were to have a fire or a giant candle, you could place this pinwheel above it and hold it over the fire or over the candle, and eventually the pinwheel would begin to turn, okay? And the reason it would begin to turn is that the heat coming off of the fire or the candle creates air currents, and it rises up when it's hot, and then as it cools down, it moves to the outside and falls back down. Convection ovens work on this principle, okay, as do those neat little things you see at Christmas time with the little angels and the candles and a little fan above the angels, right? We light the 4 candles, and then the angels spin around and they go ding, 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 ding. They hit little bells on the outside. That works on the principle of convection. Okay. Now, to really show you convection, I would need a much smaller pinwheel and a much larger heat source. Another way to show convection is simply with a piece of tissue paper and a lamp. Now, I could take my gooseneck lamp that I'm using for my radiation experiment. I could turn it so it was facing straight up in the air, and I could take a small piece of tissue paper and hold it right above it. And if I drop it, if you'll notice, it won't drop straight down onto the lamp. It will actually fall off to the side, and that's because of the air currents, the rising hot air currents coming off of the light bulb, and that is convection. Convection is hot air rising and cool air falling, and it creates a kind of this type of effect in the air. So, once again, this is Avery Copeland for Classical Conversations, Cycle 2 Memory Work, Weeks 20 and 23, Tallahassee, Florida.